Hey, today's lesson is on means. So unit 5C was about proportions. This one is about means, and it lays the groundwork for second semester here. Here's the homework. So if you haven't caught on, when we talk about a sampling distribution, we're talking about all possible samples of the same size from the same population. That's the we're repeating that. It's like the penny activity, but doing every possible combination of pennies, of 5 pennies, or whatever we're doing. So that's the idea of a sampling distribution. And if you do that, you get a sampling distribution. In this case, of the sampling of the sample mean. Here is simulated mean times in minutes from a commute. For 300 random samples of size n equals 10 from a population of employed adults. So n equals 10, and it still looks a little bit skewed here. It's not symmetric like I might think it would be. Let x bar be the sample mean in a simple random sample. If that's true, then the mean is like normal. The mean you don't have to do any adjustments to. The mean of the sampling distribution is the mean of the population, essentially, if you have every possible sample of that particular size. Standard deviation, however, for means, if it meets the less than 10% condition, then it's going to be the standard deviation of the sample divided by square root of n. And that's how you calculate it. Remember before it was like square root of pq over n kind of thing for standard deviation for proportions. So it's a little different. This is on your formula sheet. Big key is to remember to use it. Okay, so the distribution of the number of movies viewed. So when it says number of movies viewed, are we talking about means or proportions here? Seems like we're talking about means. Because it says the mean of 25.3 movies and a standard deviation of 15.8. So even though it's skewed to the right, well, let's see. So suppose we select a simple random sample of 100 students for the school. Calculate the mean number of movies viewed by the members of the sample. So we're supposed to calculate and interpret the mean of the sampling distribution of x bar. So calculate and interpret. So the mean is going to be 25.3. It's just the mean of the sampling distribution there. Interpret, if we took all possible samples of size 100 from the same population we're taking samples of movies viewed last year by students at a large high school, then the average would be 25.3. Let's see what they said. If you looked at all possible samples of 100 students from the school, calculate the sample mean, number of movies for each sample, the sample means would have an average value of 25.3. Verify the 10% condition is met. Then calculate and interpret the standard deviation of the sampling distribution of x bar. So the x bar, so is it less than 10%? So we took a simple random sample of 100 from all the students at a large high school. I'm assuming a large high school is over 1,000. So 100 is less than 10% of over 1,000. So that passes the condition. So we can then do the standard deviation using the formula. So you plug in the standard deviation of this sample divided by the square root of n, and we get 1.58 movies. If you took all possible samples of the same size, of size 100 from the same population here, the typical variation from the mean, in this case, because now we're talking about means, for the mean number of movies viewed last year by students in large high school is 1.58 movies. Typically vary from the population mean of 25.3. It's nice to say population mean. Today's move. So let's go to this website. I think it's going to help us with a big thing called the central limit theorem. So you can adjust this applet I'm going to make it right skewed. This is pretty similar to the penny data we have. If you remember the penny data, I think our mean was 19-ish, but this means 14. It's pretty similar. It's a similar shape for sure. So if we took samples of size 2, so I think this is interesting to watch. So when you do a sampling distribution, if you do it one at a time, so we're going to take a sample of 2 from the population, and then we're going to average those and plot that on the sampling distribution graph right there. If I do it again, take any 2 random samples from the population, plot the average there. Again, we're just kind of taking 2 samples, finding the average of those 2 and plotting it on the bottom there. So if we keep doing this a bunch of times, I'm going to do this 1,000 times. Okay, so the data does still look skewed right? It's a little bit less variation. So you see it doesn't go all the way out to 50 there, but it's still skewed right, not quite as big a variation. What if we went up to, say, 5? And we did 1,000 of those. It's looking definitely less variation as we've gone up. We know that's one of the concepts we learned. The skewness is going away a little bit. It's not quite as skewed as it was, although it's still skewed to the right. It's a little bit more symmetric than it was. What if we go up to 10? By the way, just so you know, I think it's kind of neat. So when you do 10 out of 10, that means you take 10 samples from the population, you average those 10 samples and plot 1 point down there at the bottom graph, the sampling distribution, what we're trying to make. If I do it 1,000 times, ooh, wow. Okay, so it did go all the way to 50. Now it only goes to like 28. Starts at, instead of 0, starts at, 5-ish. Still a touch skewed to the right, but it's getting darn close to symmetric there. Let's go 20 and do 1,000. Again, still a touch skewed to the right, but it's looking much more symmetric. Let's try 30. This is going to be interesting, actually, I think. By the way, I'm just doing more. It's starting to look almost normal. So if I kept going, again, it should look, in theory, more and more approximately normal. So somewhat symmetric and approximately normal when I take thousands and thousands of samples. Okay, so that idea, it's called the central limit theorem. So here's this is a big concept. When n is sufficiently large, we'll talk about what that means in a second, how big you have to be. As we went up, it got better and better. The sampling of the distribution of the sample mean, x bar, is approximately normal. Oh, that's a beautiful theorem. Okay, so we think even though the population wasn't normal, the sampling distribution can be normal. That's kind of interesting, actually. So if the sample population distribution is approximately normally, no matter what the sample size of n is. Okay, so what that's saying is you don't really need the central limit theorem, or you're using it a different way, I guess. If the population's normal, it doesn't matter how big the sample size is, the sampling distribution will be normal, or approximately normal. However, if the sampling size is 30 or bigger, that's our breakdown for what we need for this, then even if the population is skewed, again, even if the population is skewed, like the population is skewed to the right, the penny data is skewed to the right, the sampling distribution, as long as n is larger than 30 or larger than equal to 30, you're good, right? So it's going to be, so that's a great theorem. So even if the population is non-normal, skewed, whatever, the sampling distribution of x bar will be approximately normal when the sample size is sufficiently large. So that's a huge theorem for us. Here's the population distribution. It's skewed to the right. Uh-oh, is that a problem for us? Describe the shape of the sampling distribution for x bar with the size of n equals 5 for this population. Well, I think it's still going to be skewed to the right, right? N is not large enough to say it's sufficiently large enough for the central limit theorem to kick in. We need n equals 30. I think it's still going to be skewed to the right. So, but not quite as strong as the population distribution. So it has a little bit more symmetricness to it, if there's such a thing. But it's and probably a little less variation as well. What if n equals 100? Now you're talking about the sampling distribution will be approximately normal, right? Because n is greater than or equal to 30, 100 is bigger than or equal to 30, it would be approximately normal by what reason? Because of the central limit theorem. Thank you, central limit theorem. So here he selects 40 customers, offers them a free oil change. So Keith's budget is an average of 35 minutes per customer to complete the work. Will this be enough? Calculate the probability the average time takes to exceeds 35 minutes. Well, this is nice because n is at least 30, this data is approximately normal of the sampling distribution, right? So we know the mean is 30. Now be careful, the standard deviation of the sampling distribution is not 13.4. So it would be, I think it's, from memory, I'll tell you if I did this wrong, 13.4 over square root of, I forget if the whole thing is square rooted, I think it's just that one, over square root of 40, which is our n there. 2.11, let's see if that's how they did it. 2.11, I did have the right formula. What do we have to check first? The less than 10% condition before we can do standard deviation. So 40 is less than 10% of all the customers they saw that during that month. That's obvious. So now we can draw we want to find the probability that it exceeds 35 minutes. So we're going to draw the normal curve there. 30 was the mean, standard deviation was, I forget what it was, 2.119. So you draw it, you shade appropriately, 35 or bigger, use norm CDF. I didn't find the z-score, I did what that last step was, which is just norm CDF that guy, lower bound 35, upper bound infinity, mean is 30, and standard deviation is 2.119. The hard part is remembering the standard deviation changes there. For means and proportions, you have different formulas, but they change. Don't forget to answer the question. Because there's such a small chance of exceeding a mean of 35, Keith has likely budgeted enough time. There's a very small chance it's not going to be enough. Yes, 100%. So that's an interesting point there. So remember the averages are less variable than individual observations. Okay, so if the concept is, I like that. So as the sample size goes up, the standard deviation goes down. We've got to make the standard deviation smaller. We can't keep the standard deviation the same. The variability is less, so we divide by square root of n, and that does it for us, which is really nice. Again, the standard deviation is going to be a lot less than the population standard deviation. Pew Research asked U.S. adults how many close friends they have. Study revealed the distribution of the number of close friends is strongly skewed to the left. That's the population. The mean of 3.37 close friends and a standard deviation of 1.635 close friends. By the way, these are means, not proportions. Suppose we select a simple random sample of 50 adults and calculate X bar, the mean number of close friends. Calculate and interpret the mean. Well, the mean's pretty easy to calculate. It's 3.37 close friends. Interpret, if we take all possible samples of size 50 from the population of U.S. adults and ask them how many close friends they have, the average number in the sample would be 3.37. Sample means would have an average value of 3.37 close friends. Verify the 10% condition is met. Okay, so 50 is less than 10% of all U.S. adults, that's for sure. Now this standard deviation, it was 1.635. You would get your calculator out because these are means. It'd be 1.635 divided by square root. I think it was 50. Oh, it was 1.635. Did I do that right? 1.635 divided by, oh, I did squared, sorry. I meant to type the reason that didn't work, 1.635 divided by, I must not have hit that second key, square root of 40. That sounds better. I was trying to do the right thing, I just hit the wrong button there. And again, so we want to interpret this value. If we took all possible samples of size 50 from the same population and calculate the mean number of close friends from all U.S. adults, sample means would typically vary from the population mean of, by about 0.231 close friends. The adults in town were asked how many close friends they have. The distribution number of skewed to the left, there it is. Describe the shape of the sampling distribution of x bar for n equals 60. Well, if n equals 60, it's approximately normal by the central limit theorem. If n equals 6, it's still going to be skewed to the left, not quite as drastically as that one, and the variation will be less, but that's the idea. But not as strong. Okay. A bank must stock its ATM with cash at the beginning of each day. Based on the thousands of transactions carried out in the past year, the bank knows that the amount of money withdrawn by a customer is skewed to the right, with a mean of 87, that's interesting, and a standard deviation of 52. Because the bank estimates there will be 50 customers withdraw from the ATM today, the stocks the machine with $5,000 at the start of the day. Will this be enough money to fund 50 random withdrawals? Calculate the average withdrawal is no more than 100. So no more than 100, what we want? So we would, first of all, these are means, right? The n is 50, which is more than 30. Central limit theorems can kick in. We can prove this is approximately normal. The less than 10% condition would need to be checked. So 50 customers is less than, I don't know what the time period was. It's less than 10% of all the customers that are withdrawing for the day, I guess. Standard deviation would be standard deviation of 52, so it'd be 52 divided by square root, because it's means, 50. .35 is our standard deviation. So up there at the top, it says 7.35 is the standard deviation. 87, of course, is the mean. Do norm CDF from negative infinity to 100. If we want less than 100, right? And then put it in the standard deviation, it's 96%. Because there's such a large chance, it's more than $100. 5,000 is likely to be enough. And in 96% of the cases, it will be. So not for sure. That's pretty good. That's your lesson for today.